So now we're going to talk about the energy in the electric field. Let's imagine this positive charge here in the field due to this charged particle. As you can probably imagine, if you were to move the charged particle closer, you would have to do some work to try and overcome the repulsive forces. Similarly, if you just let this positive particle move on its own, it would move in this direction, meaning that the particle will do some work for you. What was work? Work was force times distance. So, if we recap, moving this charged particle closer this way, you would have to do the work to it. And if you were to let it go, it would move on its own in that direction. So it would do some work because it would be experiencing a force and moving a distance. That work done is very important because it's the work done by the unit charge, Q, and by that charge we mean this charge, the charge of the particle in question, that gives us potential difference, or voltage. You've come across potential difference, or voltage, when we talk about currents and the flow of electrons and electricity, and this is the actual definition. What are the units? Well, the units of work done are joules, and the units of charge are coulombs, and the units of voltage are the volt. So the volt can be defined as joules per unit charge. Sometimes this entire relationship is just expressed as energy over charge or energy per unit charge. Try this question. How much work is done moving a charge of 2.4 nanocoulombs through a potential difference of 9.6 volts? Stop the video and try and work it out. Using the formula, voltage, or potential difference, equals work done over charge. We rearrange it to give us work done equals voltage times charge to get an answer of 2.3 times 10 to the minus 8 joules. Simple. The same ideas would apply to a uniform field. But it's important to note that the energy, or the work done, only transfers when the particles move towards or away from the charged particle here, or towards and away from the plates. If you were to move a particle at 90 degrees to the field lines, perpendicular to the field, no work is done at all. These lines at 90 degrees to the field lines are called equipotentials. It's a long word, it will take me a minute to write it. Equipotentials. And you only need to cover these in the high level, but they basically state points of the same potential. So when you move between points of the same potential, there is no potential difference. But we'll come back to that idea some other time. Now we're going to talk about some very small things. We're talking about electrons, and the charge on an electron is tiny, 1.6 times 10 to the minus 19. The kind of energies that we're talking about when we describe the movement of charged particles are tiny. They're times 10 to the minus something. So a new unit needs to be introduced that will allow us to talk about the energy of electrons and tiny charges in more manageable terms. That's why you need to start using eVolts. So an eVolt is a unit of energy, just like the joule. And 1 eVolt is the amount of energy that one electron has of charge 1.6 times 10 to the minus 19 when it moves through 1 volt. So 1 eV is equal to 1.6 times 10 to the minus 19 joules. If we have 10 volts, then we would have 10 evolts, because it would be 1.6 times 10 to the minus 19 times 10. In general, the formula that you would use to convert is this one here. The energy in evolts is equal to the energy in joules divided by the charge on an electron, which is 1.6 times 10 to the minus 19. Another more common sense way of remembering it is if you have a very, very small number, so if the amount of energy that you have is, I don't know, 1.7 times 10 to the minus 36, because it's so tiny, it must be in joules. Evolts are always going to be sensible numbers. So, firstly, using the previous formula, work done over charge equals voltage. We have 3,500 volts. So rearranging, we have work done equals voltage times Q. The voltage is 3,500. The charge is the electron charge. This is a constant, by the way. You don't need to learn it off by heart. This would be on the data booklet. So our answer would be in evolts 3,500 E volts, because we have the coulomb, which is E or V. So how do we find this answer now in joules? Well, now to find it in joules, we need to multiply out this E value. So you do 3,500 times 1.6 times 10 to the minus 19, and we would get 5.6. I'll write it up here because I've run out of room. 5.6 times 10 to the minus 16. And that's your energy in fields.